Happy Friday, everybody. During this video, we're going to talk about the snowstorm across the southeastern U.S. that's going to impact portions of the southern Appalachians from far northern Georgia all the way up through the border of West Virginia and Virginia. That's going to start late night, Saturday night. At the same time, there's also going to be tornado potential across northern Florida and far southern Georgia. That's also going to be on Saturday late afternoon. We're going to be tracking that tornado threat. There you can see the 5% tornado threat across northern Florida. That's going to be from the Florida Big Bend, developing at about 2 to 3 p.m. on Saturday afternoon. A surface low is going to intensify and then lift up from northern Florida and across southern Georgia, and that's going to bring some favorable low-level wind shear and thermodynamics for a tornado threat from the Florida Big Bend all the way across northern Florida Saturday late afternoon and evening before that low-level jet moves offshore. And it's all going to be because of this surface low. This thing is going to start intensifying on late Saturday afternoon. You can see about 1,008 millibar low, and then there's going to be a warm front that extends off to the east of that, and right along that warm frontal zone you're going to have the most favorable wind shear for a tornado threat. Low level wind shear begins to maximize. You get a low level jet that develops just to the east of that surface low, and then it marches off to the east right along the Georgia-Florida border. That's where that warm frontal zone is going to set up. But we want to talk about first the snowstorm across the southern Appalachians, and then we're going to dig in a lot deeper into the tornado threat with that 5% tornado zone. Here is the latest GFS model forecast snowfall totals, and you can see that the GFS has the greatest totals a little bit further north along the West Virginia border, but it also has some big time totals too across the mountains of western North Carolina. That includes Mount Mitchell up there, Grandfather Mountain. All of those high peaks above about 4,000 feet could get double-digit snowfall totals, maybe even exceeding a foot, possibly approaching 2 feet. Some of those areas up along Mount Mitchell. You also get quite a bit of snow too across the mountains of northern Georgia. Not as much though when you get off of the mountainous terrain and across the Carolina Piedmont. It's possible that the foothills there of North Carolina could get several inches, but you're really going to require the higher terrain. The NAM's a little bit different than the GFS. The NAM actually has the greatest snowfall totals just to the west of the spine of the Appalachians, and it all depends on how quickly that surface low gets going, the exact track of the upper level low as well. The European model is further south of the upper level low, and then it bends it offshore pretty rapidly, and that's going to keep the snowfall totals near the West Virginia border down a little bit. It all depends on where that warm conveyor belt sets up and then passes over the higher terrain of the southern Appalachians. That's associated with moisture. The moisture fuels the snowfall rates, and the higher terrain is able to get high enough so you can get temperatures cold enough to support big time snowfall model. And look at that has the greatest snowfall totals right along the mountains of Tennessee and North Carolina. That's where I do think that the greatest snowfall is going to happen. And look at some of these amounts. Assuming a 10-to-1 ratio, you've got some of those exceeding about 18 inches up near Bristol, up near Johnson City, right along the higher terrain along the mountains. But I do think that this conveyor belt, the warm conveyor belt, is going to hammer the spine of the Appalachians, especially just on the east side of the mountains. This is a little bit different than those lake effect events where you get moisture and cold northwesterly flow into the spine of the mountains. That brings the heaviest totals on the western slopes of these southern Appalachians. But when you get a coastal system that intensifies to the east of the Appalachians, that brings a warm conveyor belt of moisture onto the eastern spine. You get orographic lift as that moisture is squeezed out in the form of heavy snowfall. I want to show you the upper levels here. This is the national view, and look at that bowling ball moving offshore right there. It's this bowling ball that causes the tornado threat on Saturday late afternoon and evening across northern Florida, and it also brings a snowstorm too across the southern Appalachians, and that's going to be across the mountains of North Carolina and Tennessee. Gatlinburg's probably going to get hit, as well as a little bit further north along the West Virginia and Virginia border. Someone's going to get a couple of feet of snow. It's probably going to be those locations above about 4,000 or 5,000 feet. I'm trying to decide whether I want to cover the snowfall across the southeastern U.S. mountains, or do I cover the tornado threat with that ejecting surface low in the warm frontal zone there across northern Florida. We're going to take a look at the photographs and the wind shear just ahead of that surface low across northern Florida during the late afternoon hours on Saturday. The European model is a little bit further south than the GFS model. The European model takes it offshore a little bit earlier, right near Cape Fear, and the European model brings the heaviest snow across the mountains of North Carolina and into southwestern Virginia. Virginia. And usually with these bowling ball type storm systems where they're not lifting up the East Coast, I tend to go with the southern outlier, the one that's a little bit further south. I think that you have cold air aloft, you have a little bit more mass with these bowling ball trough ejections, and the heaviest snow is going to begin late night Saturday night across the mountains of North Carolina, and that's going to continue through midday Sunday until this thing goes offshore. But definitely some southeast U.S. snowfall coming to the southern Appalachians starting Saturday night and continuing into Sunday. But this same storm system is going to have a warm sector that moves across northern Florida. A surface low is going to develop, move right along the Georgia-Florida border, and I'm going to pull up some soundings and assess the tornado potential across northern Florida too. But a lot of where the heavy snow sets up with this, I said that it's different than the northwest flow events that you get with lake effect. This is more of a warm conveyor belt type of a setup, and watch this conveyor belt lift up into the mountains. That's when you're going to get your period of the heaviest snowfall. And look at the timing. You can see the timing just on the upper left hand portion of the screen. That conveyor belt moves through the mountains late night Saturday night. It's going to be around midnight into the early morning hours on Sunday. There it is, about 9Z to 12 to 15Z, and then you get the wraparound. But that frontal genesis band where it comes up into the higher terrain and hits that terrain at a perpendicular angle, you're going to get orographic lift that's going to squeeze out the moisture. It's also going to be high enough up in elevation that you're largely going to get predominantly snowfall up in that area. And watch how the conveyor belt doesn't really push up into Maryland. I saw that there's a lot of people in Maryland, in the mountains of Maryland too up here, wondering if you're also going to get the heavy snow. The NAM model and the European model take this upper level storm system offshore at about Cape Fear, but the GFS actually sends this thing offshore up near the North Carolina Outer Banks, and I think that would bring the heavy snow a little bit further north. You can see how the NAM doesn't lift it all the way up to the Maryland border. But just as the upper level storm system goes out to sea, it's the exit strategy that there's still differences between the models. It's exit strategy as it goes out to sea. Is it going to go out to sea down near Cape Fear, or is it going to be further north out near the North Carolina Outer Banks? The NAM model and the European model take that conveyor belt with it. They don't lift it all the way up to Maryland, and that's why the heaviest snowfall totals are a little bit further off to the south, southwestern Virginia and the mountains of North Carolina and Tennessee, and someone's going to end up with 2 feet of snow up there above about 4,000 feet. So now I want to analyze the tornado potential on Saturday late afternoon, and I'm going to show you exactly when and where the tornado potential happens, but I'm really honed in on that warm frontal zone starting at about 3 to 4 p.m. This area here across northern Florida and southern Georgia, the surface low is going to develop here, and it's going to intensify starting at about southwestern Georgia as that surface low lifts off to the northeast. And this warm frontal zone is going to be the focus of greater low-level wind shear and the potential of tornadic supercells beginning at about 3 to 4 p.m. Saturday late afternoon as that surface low lifts off to the northeast. The warm frontal zone is going to lift up to southern Georgia, and that's going to bring tornado potential, and that tornado potential is going to extend down into north central Florida, southeastern Georgia as well. We're going to break down the hodograph and the low-level wind shear that's associated with that. This surface low isn't going to be a really deep surface low throughout its life cycle. This is more of a bowling ball type of a system aloft, but you still do get a strong enough surface low to excite a low-level jet in the warm sector of this storm system. So watch that surface low. It begins to develop at about 21Z, about 3 p.m. Saturday. That's going to be Saturday afternoon right about now. There's the surface low, and it just meanders up toward coastal South Carolina, and it brings that warm frontal zone along with it. There's already moisture down here, but look at that right there. Right as that front lifts off to the northeast, that's when the surface low starts to rocket off to the northeast, and then it ejects toward coastal South Carolina. Once you get that north-south orientation to the Pacific boundary, that's when you're going to get supercell storms that are going to be capable of moving off that front, interacting with the warm frontal zone just east of the surface low. Looks to me like that's going to be more of a southern Georgia event, but you definitely could get supercell storms into northern Georgia as well. Here's the HRRR model, convective evolution. And watch as that surface low ejects. You're going to see everything clear out across northern Florida and southern Georgia. That's as you get a mid-level dry slot that moves over the warm sector. That mid-level dry slot is going to clear out the clouds, allow for surface heating, that 3-kilometer cape to begin to develop. And then storms are going to develop right along the Florida Big Bend region. Look at those storms start to develop there and then interact with the warm frontal zone across southern Georgia and northern Florida. Those are going to develop first across the Florida Big Bend at about 3 to 4 p.m. There's that convective line. They're likely going to come ashore near Panama City Beach, probably near Apalachicola as well first, and across the Florida Big Bend. There's a lot of black bear actually down there, believe it or not, across the Florida Big Bend. I've never seen one, but I see a lot of the signs down there. But I do want to see a black bear at some point across the Florida Big Bend and a tornado in the same frame. It's possible that it could happen Saturday late afternoon as that convective line develops. Look at this convective line that develops right across the Florida Big Bend, and then it moves across northern Florida and the warm frontal zone of southern Georgia. That's where you're going to have pretty favorable wind shear for tornadoes and also for supercell storms. So here you can see the 850 image, and tornadoes thrive off of low-level wind shear. This is the HRRR forecast, 850 millibar winds. These are the winds about 1 kilometer just above the ground, and we're looking for when these southerlies really intensify just ahead of this 850 low. The 850 low is spinning across southern Alabama at this time, begins to eject into Georgia. Look at it intensify and blossom. You can see all the colors just erupt like a rose just blossoming in the springtime. Look at the conveyor belt, that frontogenesis band that sets up just to the north of the warm frontal zone at 850 millibars, the surface warm frontal zone at least. That is the warm frontal zone at 850 millibars. But it's these southerly winds about 1 kilometer above the ground that cause the low-level wind shear sufficient for tornado potential. And look, just ahead of that 850 low, you get the southerly winds that ramp up and then a southwesterly low-level jet that also ejects. I'm still trying to decide whether I'm going to be chasing the mountain snow event or am I going to chase this tornado potential in northern Florida. AccuWeather's already reached out to me and they want me to cover at least one of them. But boy, look at this tornado potential up near the Florida Big Bend in southern Georgia. This is the significant tornado parameter, or STP. It definitely is dependent on surface heating, surface-based cape, also low-level wind shear. The significant tornado parameter is definitely weights low-level wind shear a little bit more heavily than some of the other parameters. But notice how that warm frontal zone is a little bit limited in how rapidly it lifts off to the north. The warm front lifts just north of Jacksonville, and it's that warm frontal zone where the tornado threat is really going to focus, along and just to the south of the warm frontal zone as that surface low lifts up toward coastal South Carolina. And then it brings that favorable tornado potential offshore over the open waters of the Atlantic, over the Gulf Stream, offshore of South Carolina, where the Chinese spy balloon wreckage still might be floating around somewhere out there. Been watching that closely. Some of the recovery of the Chinese spy balloon out there just offshore of South Carolina. There's probably going to be water spouts out there that could curtail some of the recovery effort of that debris and the Chinese spy balloon. I could definitely see water spouts Saturday night across the open waters there of South Carolina. So I do want to break down the forecast hodograph. I picked a hodograph just to the north of the Florida Big Bend there. Normally I do this for subscribers only, these in-depth analyses, because we start to lose our viewership when we start to dig a little bit deeper into the kinematics here. But this hodograph, this is looking down on the atmosphere. You're looking down at it and analyzing how the wind changes speed and direction with height. And you basically will plot your wind as a vector that has wind speed and direction. The wind speed is defined by these rings. See how these rings go up in knots? There's 50 knots right there, 40 knots, 30 knots, all the way down to the surface. This is your storm motion right here. You have a northeasterly storm motion at 35 knots. That's at least what's being predicted by the model. And basically you plot it from the origin, the direction that the storm is moving. And it has a direction due northeast basically, and it's just shy of 40 knots. There's your 40 knot ring. That's northeast at 35 knots. That's a manageable storm motion for chasing. Your surface wind is southeast at about 10 knots. So it's anything in this quadrant over here is going to have an easterly component, and your surface wind there is southeast at about 10 knots. Your wind just above the ground at 1 kilometer then is out of roughly the same direction and then increases up to 40 knots. And that creates 0 to 1 kilometer bulk shear of about 30 knots. You basically subtract the vector at 1 kilometer from the vector at the surface, and that's how you get your 0 to 1 kilometer bulk shear vector. And if you can imagine a wind 1 kilometer above the ground that's faster than your surface wind by 30 knots, that's going to excite horizontal spin in the atmosphere that is perpendicular to the shear vector. The shear vector is the difference in those vectors. It's oriented like that, and that's going to excite horizontal spin that is oriented perpendicular to that shear vector. You can just imagine one hand moving in one direction, this hand moving in that direction. That's going to create spin that is oriented parallel to my image here. Perpendicular to my image. And so if your storm motion is oriented parallel to those low level, that spin in the low level shear, then that's called streamwise vorticity or streamwise spin. So if you had a storm motion vector that was oriented perpendicular to that shear vector as well, because you know that the horizontal spin is also oriented in that direction, then that storm is going to be more effective at flipping that spin into the vertical and causing tornadoes. That's very generally how tornadoes happen. You're basically just tilting horizontal spin into the vertical by an updraft. And when that updraft is rotating like a mesocyclone in a supercell, then it's capable of a stronger updraft. And when you're capable of a stronger updraft, you're going to be more effective at flipping that horizontal spin into the vertical. And that's determined by your critical angle. That's the angle that your storm motion vector makes, or that's the angle that it makes as you take the tip of the storm motion vector and draw it all the way to the base of your shear vector. This is your 0 to 1 kilometer shear vector. That's your low level shear vector, and the angle between that the tip of the storm motion vector makes with the base of that shear vector, that's your critical angle. My office mates at the University of Oklahoma came up with that critical angle term, and the closer that angle is to 90 degrees, the more likely the storm is to pull in streamwise vorticity at the low levels and then more effectively flip that into the vertical and get tornadogenesis. There's a couple factors that determine how likely tornadoes are that are going to happen. It's how long the shear vector is. When it's greater than about 20 knots, that's enough horizontal spin in the low levels of the atmosphere to get launched into the vertical. Also, your low-level storm relative inflow, basically how long this line is from the tip of the storm motion vector to the shear vector, the low-level shear vector. If this line is really long, then you're getting a ton of storm relative inflow. You get a lot of mass, a lot of moisture into the low levels of the storm. You also get ventilation aloft by the fast mid and upper level flow aloft. That's evacuating mass from the updraft. And two things determine how big a storm is: your low level inflow and the evacuation of that mass aloft in the upper atmosphere. If you have a little bit of a damper in the upper atmosphere, that can be caused by a gravity wave, maybe during the winter time when your troposphere is a little bit lower too. That can lead to a little bit greater mass of a storm, even though you may have a little bit less low-level storm relative inflow. But the length of that vector, that's important for a low-level storm relative inflow. But also the outflow aloft, the ventilation of that updraft determines just how big and how much mass that can attain. You've also got a little bit of negative storm relative helicity contribution. When you get this concave that's oriented in the other direction, that's negative helicity, but studies have shown that that negative contribution between about the 2 and 5 kilometer layer is irrelevant, especially when you have a pretty long low-level shear vector like you have here. The stronger a low-level jet, or that 1 kilometer wind, when it gets up to like 50 to 60 knots, then you have a really long shear vector that could be even longer than 30 or 40 knots between 0 and 1 kilometer. And then you can more easily compensate for shallower critical angles, or those critical angles that are a little bit less than 90 degrees. Overall, this sounding here looks like it's marginally supportive of a tornado threat, especially if you can get some easterly winds. More easterly winds near the warm frontal zone, like if you had more of an east-southeasterly surface wind, that might change the orientation of your vector, though. You might even have a more shallow critical angle, and then that storm might be a little bit less effective at pulling in streamwise vorticity and turning into tornadoes. But a hodograph like this, in general, when you have a hook-shaped hodograph like that, the wind shear is supportive of sculpting that supercell into a tornado producer. In the southern hemisphere, they'd be oriented the other direction, a hodograph that's supportive of tornadoes. And if you have a more straight line hodograph, just one line from point A to point B, then that equally favors the left and right movers. And a lot of times you're not going to get as much in the way of tornadoes. But you really need that hook-shaped hodograph to favor tornado production. So to me, it looks like I probably should target the tornado threat across northern Florida. The Storm Prediction Center, the new outlook that is coming out, breaking news of that 5% tornado threat does cover a large swath of Florida, from the Florida Big Bend all the way up to about the Florida-Georgia border right near Jacksonville. And that's because that warm frontal zone doesn't really invade Georgia too much, even though the surface low does lift off to a little bit to the further to the north. There's just too much rain, too much precipitation just to the north of that warm frontal zone, and that's going to prevent its northward lift up into Georgia, and that should keep the tornado threat down into Florida. But boy, it looks to me like it noses into far southern Georgia, definitely on the 12Z models. I would certainly expand that 5% into southern Georgia, just realizing that surface low is going to be intensifying as it meanders northward up toward coastal South Carolina. I do think that it's just that low-level jet's going to intensify enough to bring that warm frontal zone into southern Georgia. So I do think that the greatest tornado potential is in the southern couple of counties of Georgia, but also the southern couple of counties in Florida. And then you're going to get more veered out wind shear across the southern half of that 5% tornado zone. But definitely the southern Appalachians, in the higher terrain above 3,000 feet, a snowstorm is basically a certainty up there. Topography is a constant in any forecast. The topography is known, so even if you have a lot of different scenarios with a surface low track around that, at least one thing that is constant is the topography, the presence of orographic lift. And you go up above 3,000 feet, you're likely going to have temperatures that are cold enough and supportive of snowfall.